welcome to this second session of our PV Magazine Digital Roundtables. The first time we are putting on digital events, but of course, not the first time we're put on the Quality Roundtable. This is the Quality Roundtable session, and in fact, it's got a pedigree back to 2015 and has been held over the years on 5 continents by PV Magazine editors and various members of the team. And why is that? It's because quality in PV remains an absolute key discussion, making long-lived assets that are going to not let our industry, not let investors, and also to maintain our efforts in the fight against climate change, to enable the energy transition. We don't want to let any of the stakeholders down. Now, not to let you down today because we can't have an in-person event. We still have lots of the great functions that we have in an in-person roundtable event on this digital platform. You may not have used an event app before if you're just joining us, if you weren't in the first session today. So here's just a couple of pointers as to how you can find your way around the app. There is an info booth, and we have people staffing that. If you have any problems with it, of course, refreshing the browser is always an easy solution. There is video networking available in the Zoom room, a Meet the Speaker Zoom room, some group discussions, and even attendee-to-attendee chat function. So I encourage you all to get involved today, to be a part of our Quality Roundtable event. And please do also send through your questions. We're going to have a very interactive discussion towards the end of this session, particularly focused on floating PV. But getting more into the content now, Marian Willum, who is a PV Magazine editor, I'm sure many of you have read his work, has put together a really exciting program of quality discussions going right across the value chain in PV. So Marian, tell me a little bit about it.
Well, thank you, Jonathan, for this introduction, and welcome everybody also from my side. Yeah, I have been busy putting together the content for this session today, and our main talking point will be venturing into new technologies and managing the risks associated with them. And we'll start with the debate on landing larger wafer formats, as they have been enabling high power modules with beyond 500 watts power rating. It will be definitely interesting to get this input and see how cell cracking can be avoided in this environment. And also we will talk about light-induced degradation. There is a solution, gallium doping, during the ingot pulling process that promises to prevent this issue that has plagued the industry. And also we have a panel discussion coming up on floating PV, one of the highest growth markets there is in photovoltaics, with more than 150% growth as determined by IHS Markit recently. And we will hear how to mitigate risk of power electronics and equipment that's susceptible to corrosion on water or near water. But all of that is going to come later, because now we will start with single-axis tracking and wind effects and wind instabilities, because the best value proposition of bifacial modules is if you arrange them on a single-axis tracker in a 2- and portrait solution. But that brings a lot of challenges, as you have been finding out, Jonathan.
Indeed, and Quality Roundtables always have case studies, so I'll be presenting the first one, as Marian said, on single-axis tracking just after this. Well, yeah, the first case we're discussing today is in my home country of Australia. This is in Queensland. It's the OKI2 project near the regional city of Toowoomba, originally planned for 55 megawatt, but mentioned or listed by the owners, which are the Foresight Group, as a 70 megawatt project. It was acquired by Foresight for their solar fund from Canadian Solar for $55 million. Here's a quick timeline of the development of the project. It neighbours the OKI1 project, which is a smaller project. And importantly, on this timeline, we can see that there's been 2 weather events that have actually impacted on the project, and we're going to look into how it has impacted on the project. There was a storm in October 2018 where winds went up to 46 kilometres an hour, which may not seem too high, but this weather station was 10 kilometres away from the array. The EPC Canadian Solar was very keen to point out in comments to PV Magazine that the site was still under construction when it was hit by that storm. And here's some of the damage. These are the photos. We've been able to get photos from a number of sites, as is often the case with PV projects. The wagons have circled, and the project participants are not always very keen to talk about what may have gone wrong. But from the source, from the photos that we've been able to source, we can see a number of effects of this wind on the tracker array. In particular, we can see the torque tube at some of the positions is actually twisted, is actually bent. We can see that the damage is particularly pronounced towards the end of each row, which may be illustrative of what caused this event. And then also some of the posts themselves are actually bent and appear to have come free from the ground, or not free, but at least loose in this particularly troubling soil at the OKI2 site. Now, reports were that about 1% of the modules were damaged. That was from a public authority in Queensland, so that's about 2,000 modules. But that doesn't also count those that were damaged, perhaps cells cracked and these kind of things that will only turn up over time. Canadian Solar advised in 2019 that the project was being electrified towards the end of that year, but Foresight in their latest annual report still list OKI2 as being under construction. And they also mentioned this second storm event. Here we go. That was in January 2020, which affected 15% of the site. Now they say the site's not going to be fully operational until the end of 2020. In terms of its operation to date, we can see OKI2 is the red dotted line there. OKI1, the smaller plant next door, is actually performing. These charts are from Rystad Energy in terms of performance ratio. And we can see OKI2 was starting to be electrified kind of towards the end of 2019, sorry. So we're talking about September, October, November, and then this little decline at the end. You shouldn't worry about that. That's just autumn arriving in Australia. Another chart from Global Roam. This is from their NEM Watch, which is an excellent service that Global Roam supply about the Australian national energy market. We can see the output data or the performance data from the OKI project. Here we go. The dark yellow bars here are the average daily output. The light yellow is the peak output. And so we can see that OKI was held at this very low hold point. It's called as a part of the AEMO, the notoriously fussy Australian grid operator, as part of their commissioning process or their GPS process. And then it was starting to step up towards the end of the year. And then we can see in May of this year, production completely stops. Why? We're not really sure. Why is OKI no longer feeding electricity into the grid? And just to give you an idea as to the financial losses that may be being suffered by the owners, this pink line is the average wholesale electricity price in Queensland on each of those days. So this is all revenue on top of certificate revenue that's being foregone by Foresight because of this range of problems. There was a range of problems. But what is behind it? Was it the tracker structure itself? Was it the ground conditions themselves? Was it the location? We know that it was a storm-prone area and also located on a floodplain. And to what extent has these two storm events impacted on the commissioning process, which is clearly costing everyone money? Now, in terms of the single-axis tracking system itself, we're going to look at those in much more detail next when Marion joins the stage and has a conversation with two of really the world-leading experts in single-axis tracking arrays, wind tunnel design, and wind effects of trackers.
Thank you, Jonathan. A truly, absolutely horrific site, and it must be an absolute nightmare for Foresight. Well, my next two guests, you're right, they're leading experts on the field of single-axis tracking and the wind instabilities. We have their job it is to make these incidents not happen anymore in the future. I have David Banks, a well-renowned wind testing expert at CPP, who is also just got announced the president of the institute at the start of this year. Thank you, David. Hello and welcome.
Hi, Marion.
And
good morning.
I also have Thorsten Krey, who is the head of building aerodynamics at the Institute for Industrial Aerodynamics Aachen, who has also tested and validated a huge number of solar systems, including trackers. Hello, Thorsten.
Hello, Marion.
Well, Torsten, what are the forces that are at work when wind blows over a 2P tracker? What do we have to understand about the mechanics of the whole problem?
Right, I do have a little presentation that I would like to go through, so I hope that my screen is now being shared. And is it? Right, there it is. So the presentation is entitled Wind Effects on Single-Axis Trackers and Possible Stow Strategies. Wait a second, I cannot move on the slide. Okay, there it is, at least on my screen. So on the left-hand side, there is a model of a single-axis tracking array as used in a pressure study. And what we will test in tunnel are different tilt angles, row spacings, and row positions. And the outcome of the raw data analysis would be static and dynamic wind loading for several load effects, such as peak torque, which is relevant for the design of the torque tube and drive post, or peak normal load, which governs the design of posts, torque tubes, spans, and so on. So let's take a look at the torque over tilt first. And what we can see is that for a perimeter row, the torque is highest at the 0-degree tilt angle and then decreases with increasing tilt angle. While for interior rows, the torque peaks rather at 10 degrees. But the normal load effect is just opposite to that. So what we can see for a perimeter row is that there is an increase of normal load with tilt angle, and it is highest at the largest tilt angle. And for the interior rows, the trend is a little bit different due to sheltering effects. The peak normal load rather occurs in the medium tilt angle range. And that is an optimization problem because we have one load effect which gives the best result at 0-degree tilt angle or at low tilt angles, and the other one is optimized at large tilt angles. But the design of single-axis trackers is further complicated by a phenomenon called torsional instability. At flat and low tilt angles, the mitigation of this instability can only be effectively done by increase of stiffness, while at medium tilt angle, mitigation is also possible by increase of damping. And only at large tilt angles, I would say that torsional instability is usually not of concern anymore. So just to wrap up, stowing flat does have advantages in terms of static and dynamic wind loading. It's actually more economic overall, but the risk associated with torsional instability is higher and the instability is more difficult to control, which is why there are also good reasons for stowing at medium or even high tilt angles. Possible countermeasures to torsional instability are the increase of torsional stiffness, of natural frequency, and or of damping, or a combination of these. And what we're also currently seeing in the market is that torsional locking mechanisms are coming up more and more. And with that, back to Marian and David.
Well, thank you, Torsten. For this introduction to this topic, and you spoke about some of the solutions that manufacturers have to address this issue. And David, maybe you can tell us a little bit about, do you think what the solutions are, and if they're all equally feasible financially and technically to prevent this torsional instability from happening?
Well, so they're all feasible technically. The challenge, of course, is financial, right? So when you say increased stiffness, as Torsten mentioned, if you're going to achieve that solely by increasing the thickness of your torque tube, I think you'll quickly find it's cost too much. So then you can increase stiffness by essentially locking it out at every post. Now you've got the cost of the locking mechanisms. Conversely, if you want to stow at high tilt now, your foundations are going to cost more. You'll be higher normal loads, overturning moments. And depending how high you tilt, you're going to need dampers, and how many dampers. And now you've got the issues of the cost and maintenance of those. So there are solutions, but none of them are free.
Thank you for this assessment. And Torsten, what do you think? What is a best suited solution of the four that you just mentioned to address this issue?
Well, as David mentioned, in the end, it's a question of cost. But from my viewpoint, from a safety viewpoint, I would prefer torsional locking mechanisms, because these can effectively transform a single-axis tracking system into a fixed tilt system. Fixed tilt systems don't have issues with the instabilities.
And we have covered this issue at PV Magazine before, and I know that there was a lot of debate around stowing at 0 degrees with 1P trackers, and now with the 2P trackers and one of the four solutions that you just mentioned. Is there a change? Do we need to reassess whether to stow at 0 degrees or at a high tilt or low tilt angle?
I definitely think so. Because as I mentioned in my presentation, I would say that the static and dynamic wind loading gives the best result at flat tilt angle at or about 0 degrees. And the problem with that tilt has always been the torsional instability that can occur, and that has led to damage, as Jonathan has shown. And this conclusion is changing now because of the torsional locking mechanisms that are coming up more and more. So I would definitely say that with a locking mechanism, or also with other mechanisms such as using very short rows, stowing at 0 degree, is possible. It just takes more effort than stowing at high tilt angles.
And David, do you share this assessment? Do you think that stowing at a low tilt is an improvement here?
I've long cautioned about the risks of stowing at a low tilt, and you'll notice we're referring to the torsional instability in very generic terms, instability, and that's because there is some ongoing discussion of what the correct terminology would be, sometimes referred to as galloping, sometimes it's referred to as divergence. And that detail of the language has to do with what solutions might or might not work. And for divergence, certainly increasing the chord length increases the risk. And so it becomes harder to make a 2P work. That said, I think locking out, it does work. You just need to know how many places you have to lock out. So that's going to affect your cost. So that's what you're studying now, is just how many, how often are we going to lock the thing out.
Okay, and a last question, just a quick fire closing statement, basically. In other industries, like in bridges or skyscrapers, we do have international codes that prescribe how these buildings have to be built, and we don't see them so often being destroyed in the wind anymore. For single-axis trackers, there's no such thing. Should we have it, or is it us holding back as an industry?
I'll go first. I think we should have performance-based codes. I do think there needs to be a place to put information, but I'm not a big fan of prescriptive codes that would require a specific set of tests, because I think this is a very rapidly evolving industry, and if we write a specific set of tests that make sense now, they might not make sense even in a year and a half. But I would like to see the knowledge gained from some of these failures make their way into at least a loose set of standards, if not a building code, then perhaps an insurance industry document or a bankability document.
Okay. Thank you for this assessment. And I get a question from the audience that I want to forward. And so we have an engineer who says he is more interested with risk or in risk than with cost, and asks if fixed installations are less susceptible to these problems, a trade-off of performance for reduced risks. So what do you answer to that? And I open the question to the both of you, maybe starting with Torsten at this stage.
Yeah, fixed tilt systems are also susceptible or prone to vibrations, I would say. They can also suffer significant dynamic amplification of the static wind loading, but they're not prone to torsional instability because there's no moving part such as a torque tube. So overall, yeah, fixed tilt systems offer more safety because of that. But the single axis tracking industry is working hard on fixing that problem. I think that everybody's aware of the failures that have taken place, and with torsional locking mechanisms, I think that single axis trackers can be ultimately as safe as fixed tilt systems.
Okay, thank you, Torsten. And we are running a bit out of time, and I do thank you both for joining this discussion today. One question we got from the audience, which has been up the screen, is whether you can have the decks presented after the session. Yes, definitely. Yeah, we will make everything available. No worries about that. It's in this app. And you can see it later on. David and Torsten, thank you so much for your time and for informing the PV industry today once again with your insights from the wind tunnel. It's been an absolute pleasure.
Thank you for having us.
A lot to process there from a completely different field of wind dynamics. And my next guest, well, he is an alien to it. He has been in the tracking industry for over a decade, and he has seen lots of input from the wind tunnel experts and how they shape product design to mitigate all these wind instabilities. James Butcher is a project engineer with Nextracker. And well, James, are we on to the next big development, the market-shaping development that the PV industry is seeing right now?
Thank you, Marianne, for that introduction, and thank you to Professors Banks and Cray. It's humbling to be included as part of this panel with David and Thorsten. And I do see that with torsional locking mechanisms coming into the industry, they're offering much better solutions to counter these dynamic effects. So specifically torsional galloping, I think it's great that many more people in the industry are becoming familiar with this term. Unfortunately, the increasing familiarity with torsional galloping is typically coming about from when things go wrong, and we see failure events like what happened at OKI. I'm sure everyone has seen other videos on social media with trackers flapping around and panels flying away. So I wanted to jump straight in with one of those examples of what can go wrong with tracker dynamics, specifically with a two-piece system. And what you can see here is that looking at the cardboard on the ground, the boxes are not moving or blowing away. This is not like what you'd see on the Weather Channel in a storm where you see umbrellas flying. This is a low wind speed event, but the resulting effect on the tracker is significant. And what this shows is that typically everyone focuses on extreme winds or ultimate design wind speeds when designing for structural capacity. But it is low wind speeds which can also result in torsional instability issues and tracker failures. Considering that low wind speeds are going to be occurring much more frequently, understanding instability at low wind speeds is critical for avoiding these types of failures. This is a further example of a major wind event from another Spanish project at a location which is subject to the Cerroso winds, which are higher wind speeds and more frequent high winds. Thinking back to the motion which we saw in the first video and comparing to the type of damage we see in this photo here, or like what Jonathan was showing from OKI, imagine just how violent the tracker movement would have had to have been to result in the structure being torn apart. Looking at this photo, you can see that the damage is not isolated in a small area, but continues along this row and the next, and it appears to extend further into the site. So this damage is extensive, similar to OKI, where you see damage across a wider area of the site. So for a site which is expected to regularly experience these types of winds, it's reasonable to expect that failure events will continue to regularly occur with this type of tracker architecture. We see solar farm project design life has extended from 25 years to 35 and even 40 years. And so over that time, how many failure events would occur at sites with regular winds because these trackers do not sufficiently mitigate torsional effects? In addition, how would you remediate this damage if you were repairing or replacing with the same system design? For this to have occurred, there's a fundamental issue with the design, and we believe that this comes down to poor understanding of dynamic effects or insufficient design to address these dynamic effects. You can't go out and rebuild this system like for like if you're going to experience these types of winds multiple times a year. That's multiple failure events every year over 30 or 40 years. So why then are these failures still happening? Every tracker company should understand wind dynamics, and wind tunnel studies are now a normal part of the design process for most systems. However, what we see is that not all wind tunnel tests are created equal, and that there are multiple wind dynamic effects at play. Another issue is the understanding of wind dynamics and how they interact with trackers has developed so much in a short period and continues to develop, with recent studies highlighting that there are multiple dynamic effects to consider, so the design methods for these systems should also continue to develop. Thinking back to 2014-15, the tracker industry was taking off, and the approach to designing trackers was, well, this structure doesn't fall within design codes, but let's assume it's like a slope roof, which we do know how to design, and so the approach was horizontal stowing to minimize wind loads. Then in 2015, 2016, CPP and Next Tracker with David Banks here, we investigated torsional galloping and updated our system design to address this. Since then, we've seen that there are actually multiple wind dynamic effects and that not all these effects are considered in tracker design within the industry. Torsional galloping is the buzzword now because of bridge sectional design and suspended bridge decks being prone to galloping. Everyone has seen the Tacoma Narrows Bridge, which tore itself apart, which was a galloping or frequency-based failure. But trackers are not bridges which have high fixity at each end. And so designers are seeing dynamics, but missing completely different dynamic modes. Whilst wind tunnel studies are essential for assessing dynamics, the studies need to include full aeroelastic tests instead of just sectional tests, like what is done for bridge design, and these wind tunnel results need to be peer-reviewed. In this video here, you can see the different action, which is more like a waveform than what we saw in the first slide, and this is what we would actually call torsional galloping. So the first video is what we now would call torsional divergence, and torsional divergence is what is being most missed in tracker design. And so divergence is an instability that is caused mainly through reduction in net damping of the system, such that when this net damping goes below zero, energy is pumped into the system instead of being taken out by the dampers. And then there's a third dynamic effect, which is vortex lock-in or torsional flutter. This is a high tilt instability, which is amenable to damping. With Next Tracker's 1P tracker Horizon, we address dynamic effects with high tracker tilt stowing and damping, but with 2P, the loads are so much higher that this is not a viable solution. There are many ways to solve these issues in system design, but we see no amount of economical stiffness and damping can resolve this with 2P or will prevent the failures we've seen. That's why on our 2P tracker NX Gemini, we've implemented a locking actuator at almost every pier. The previous video showed trackers relying on stiffness and damping to address dynamic effects, and we know that that's not enough. Otherwise, these failure events wouldn't be happening. For 2P trackers, a locking mechanism is essential to counter dynamic effects. With Gemini, we've removed dampers and replaced them with locking actuators, which has significantly increased system stiffness without damping, and our wind tunnel studies validate this approach and show tracker stability against the multiple dynamic effects. We've clearly seen what can go wrong in the industry where poor design results in tracker failure. Designing for multiple dynamic effects means that locking mechanisms are critical to maintaining system stability for 2P systems. Using cheaper solutions without this might save a couple of dollars of capex up front, but with that small saving, you're gambling on an unstable design, and all it takes is one wind event to put the project out of action at significant cost. And OKI is a perfect example of just that. In summary, it's great to see how far understanding of dynamics has come, and I look forward to greater adoption of this design approach in the future with torsional locking mechanisms, and that's why we're saying at Next Tracker to keep it locked.
Thank you. Thank you, James, for this insight and update on the new product and how the theory or the theoretical underpinnings which have been developed in the wind tunnel have found their way into the market to secure installations and secure investments. Thank you very much. Moving away from the topic of trackers and wind instabilities, we are now walking towards the module section of this session. Light-induced degradation, a problem which has been haunting the PV industry since its inception, basically. And it can affect modules by, can cause a performance loss in the modules by 1 to 3% within the first year. Well, it's too little for the performance insurance warranty to cover the damage, but it's too much to actually be ignored by the stakeholders. Just imagine a 3% performance loss on a 300 megawatt installation. The damage is easily within the millions. Well, one way to address this issue is by taking out the element that's actually causing it, because it's caused by the boron-oxygen complex. Well, taking out the boron and then replacing it with gallium is promising and has been resurfaced as a solution after a cross-licensing agreement has been done by LONGi with Shin-Etsu. My next guest, Monsoon Wang, is the product director of module manufacturer LONGi. Hi, Monsoon.
Hi, it's okay. Okay, can I start now?
Yes, I can hear you.
Okay, so I can start now, the presentation.
Yes.
Okay. Okay, thank you, everyone. Good afternoon, everyone. Friends from Europe. So this is Monsoon Wang from LONGi Solar. So it's my pleasure to make this presentation for you. So today, my topic is gallium doping, the best solution for LID. So my presentation includes 4 parts. The first, we focus on the gallium doping and the gallium doping wafer. Second, in a quite brief introduction about the LONGi solar module's quality. The third part is about the bifacial module of LONGi Solar. So finally, about the key features of Hammerfall, the new product of LONGi Solar, which will be launched immediately. So first, let's focus on the gallium doping technology. So as we all know, that LID often occurs in the PV module. So LID means light-induced degradation, the degradation caused by the light soaking. So now it's very clear. So for the industry, we made a lot of research. Now almost everyone is clear that the LID in the P-type silicon module is mainly correlated with the boron-oxygen complex. So as we know, boron is the element which used as a dopant in the P-type silicon wafer. Also, during the production procedure, we got some oxygen remained in the silicon wafer. So in the light soaking, so the boron and oxygen combined to the complex. So that boron-oxygen complex can generate the recombination of the minority carrier in the silicon wafer, which will reduce the efficiency of the cell. So that caused the degradation of the module. So we also know that the boron-oxygen complex defect is related with the concentration of the boron and oxygen. The higher concentration of the boron or oxygen, the higher degradation it will cause. So also in industry, we studied a lot. So we have some solution for the LID. The main way is to use high temperature illumination or the forward current to regenerate the cell efficiency. These 2 methods are quite mature now and widely used in the industry. So it's effective on the LID of the P-type silicon wafer. But we have a better solution, actually. So the way is use gallium doping wafer. So as we know, gallium with and the boron, they are also, gallium are also the trivalent element. It can be used instead of boron in the P-type wafer as a dopant. So if we use gallium as a dopant, we can avoid the boron oxygen complex defect. So this will help us to reduce the degradation of the cell. So as we studied that in the room temperature, if we use a gallium doped wafer, there's nearly no degradation of the cell, which shows in the picture of the left side. In the left side, you can see that if we use a gallium doped wafer in the room temperature after long time light exposure, the efficiency keeps very stable and almost no degradation. But also we find that if the temperature is high enough, we still have some degradation even we use a gallium doping wafer. So the mechanism is not LID, it's related with LETID. LETID, which means light enhanced temperature induced degradation, is some kind of LID occurred in high temperature. So the mechanism of LETID is quite complicated. Some research institute, such as UNSW, thinks it's related with hydrogen, and also some research institute thinks it's related with impurity in the silicon wafer. So, but which means that we need better quality of wafer to reduce the LETID phenomena. So we also made some tests compared with the LETID in gallium doping wafer and the boron doping wafer. It can show that the results shows that by using gallium doping wafer, we get much better, we get much lower LETID compared with the boron doping wafer. So this seems like the picture in the right side. You can see the degradation rate, and the degradation is lower if we use gallium doped wafer compared with the boron doped wafer, boron doping wafer. So, which we can get conclusions that by using gallium doping wafer, we can not only inhibit the LID, but also the LETID can be quite reduced by gallium doping wafer. So this page is about advantage of the gallium doping silicon wafer of LONGi Solar. So although the doping wafer has a better quality, but in the production procedure, it's not so easy to control the quality since the for the gallium element, the segregation coefficient is higher than the boron, so it's not easy to control the resistivity of the wafer. LONGi Solar worked on it for quite a long time, so till now we get a very good result on it. So for LONGi, we control the resistivity of the wafer very well. So the range is from 0.3 to 1.5 ohm, almost the same with boron doping silicon wafer. So we can provide corresponding resistivity products according to the customer they demanded. So also for the cost of the gallium doping wafer, we get almost the same cost compared with a boron doping wafer. So we are selling the wafer at the same price to the industry. So we get some very good feedback from our wafer customer. Not only the degradation is lower, but also the cell efficiency is a little bit higher. We can see it on the picture of the right side, you can see that if we use gallium doping wafer, we get higher cell efficiency. So it's about 0.09% higher than the boron doped wafer. So this picture also shows LETID results from the cell manufacturer. You can show on the 60 centigrade, the degradation of the gallium doping wafer is lower. Also on very high temperature, 75 centigrade, the degradation rate is also lower and the degradation is lower. So all these results shows that gallium doping wafer have very good benefit. So if we use gallium doping wafer, so we can get a better, better degradation result. So we have the better quality warranty for the gallium doping wafer product. So the first year we guarantee the degradation is less than 2%. That's a quite good, warranty in the industry. So the second part is about the product quality. Of LONGi Solar. So we did a lot of tests in the third-party institutions all over the world. So in ITC, the 2019 PV Module Index, LONGi Solar got the High Achiever Award companies for the test. So the test is about reliability, such as DH, DML, PID test, and the performance is related with the PCD, PCT, efficiency, and pan file and LID. Also the material quality test. So we get a quite good result from all those tests. Also in the PVEL and DMVGL quality test, we are the top performance manufacturer. So we passed the multiple times IEC reliability test, and also we get the top performer award from 2017 to 2020. So from 2017, LONGi Solar started to promote the bifacial double glass module to the market. So till today, we have shipped over 5 gigawatt bifacial module. So it ranks #1 in the industry. So our bifacial module have been applied in the projects all over the world. So the energy yield and the reliability had been verified by our customer. So today the main product of our bifacial is a Hammerfall module. Now it's seen as the most bankable bifacial module in the industry.
Thank you, Monsoon, for this input. It's been incredibly interesting and surely interesting to see where the industry is moving with P-type doped wafers. Just a very quick question from the audience before we're moving on. The audience are wondering what percentage LID does LONGi assume for PV cyst for its gallium doped products?
Basically, we assume it as 1.5 in the first year, or maybe some, in some circumstances, 1% is also okay.
Okay.
Yeah.
Thank you, Monsoon, for your time. That's been incredibly interesting. And now we're moving on. Thank you. At the start of the year, many module manufacturers have announced new products. And for the first time in the PV history, these new modules went well beyond the 500 watt mark. And this has been achieved using larger format wafers, where the standard wafer came with 156 millimeter per side. We are now moving well beyond 200 millimeters, 212 or 222 millimeters are making their way into the industry. Well, a wafer is a 0.3 millimeter thin and made from silicon, which is incredibly brittle. So it's incredibly susceptible to micro cracks. One company that has put out such a module will be presenting now. We have Craig Snee from ETS Solar. He's the technical sales director, and Craig brings with him 10 years of experience in module manufacturing and material technology. Hi, Craig.
Yeah, hi everybody. Thank you for the introduction, appreciate it. So my name is Craig Snee, Technical Sales Director at ETS Solar. Before I begin, I guess I'd like to thank PV Magazine for hosting this event, uniting all of us from around the globe, a fantastic accomplishment considering today's climate. I'd also like to recognize the remarkable resiliency of our industry, which continues to shine in these challenging times, continuing to push forward quite impressively. ETS Solar has continued to push forward as well. Despite the economic and industrial instability, we've continued to grow as an organization with a focus on sustainability and excellence and innovation, process improvement, and quality. And actually, just earlier this year in April, we opened a gigawatt facility for manufacturing PV cells and modules in Cambodia. So I'd like to talk a little bit about ETS Solar, and then I can get into the details about how we're manufacturing our large format cells and the processes that are related to instill the quality that is needed for this industry. So ETS Solar was founded in 2005, one of the first module manufacturers and solar companies in the industry in China, and went through a corporate restructuring in 2018 with establishing our global headquarters now as ETS Solar Power in Hong Kong, and established ETS Solar Inc. as our sales entity. Since 2007, ETS Solar has deployed over 7.2 gigawatts of panels around the world with over 1,500 different partners in 80 plus countries. We have a global network that expands the globe here, and 2 manufacturing facilities for module production and cell production in Vietnam and Cambodia, with actually a sales office in Munich, Germany. So ETS Solar has 2.6 gigawatts of cell module production and 1.6 gigawatts of production capacity between our 2 facilities, and that continues to grow. This vertical integration helps us to be more flexible and to address a global market. We have exacting control systems pushing for excellence in quality standards and assurance. So our vertical integration enables cost savings, reliability, and lowers our carbon footprint. We're affiliated with the top quality manufacturing with meeting the standards of IEC, TUV, UL, ISO, and others. We continue to innovate throughout our processes and products, offer a highly automated manufacturing facility with high reliability, repeatability, and quality, and employ FMEA approach to manufacturing, monitoring all processes, looking for areas for continued improvement and to ensure quality. We're one of the more reliable choices in the industry with leading quality standards of UL, CE, VDE, and others, and offer excellent yield performance and offer support to the entire life cycle of the product. Under one umbrella, we offer numerous professional endorsements, TUV, CE, VDE, PV Evolution Labs, factory certifications through Lowe's, CEA, Solar Buyer, and others. Now, speaking on innovation, and what was just touched on as an introduction here is the development of the cell formats becoming larger in time. And this kind of gives a snapshot of where the market was and forecast to where it's heading, thanks to PV InfoLink. So in 2019, Q2, wafer sizes saw a growth from the 156.75 millimeter M2 format, shown in gray on the chart, and have evolved to a 158.75 G1 format. And also throughout the 2019 was introduced an M4 format with 161.7 millimeter size square. The resulting module power jumped from somewhere in the 375, 385 watt range to 400 watt plus for 72 cell modules. And as early as 2020, this year, Q1, module manufacturers began using even larger format cells, ranging from 166 millimeter M6 format to the G12 format of 210 millimeters. So these are becoming more of the standards in the industry. The trend shows that this is an adopted technology, something that's going to happen immediately. It has done so in 2019, 2020. You can see that about 75%, more than 75% of the industry will be using these larger format cells and continuing to go to even larger. It's a pretty incredible trend, and within, let me see, I guess about 4 years, you can see that the module that our manufacturer will be utilizing about 80% of the modules or higher will be utilizing these large format cells. So with these large sizes of format of the cells comes some challenges. There's some mention about it being brittle, micro cracks happening, and how to actually manage these through the manufacturing process, the handling of them, as well as the trend for cutting the cells into smaller sizes and doing whether it's tiling or something along those lines for the format within the cell, the smaller sizes are utilized. So ET Solar is now producing a 530 watt 72 cell bifacial module. This is utilizing M7 cells. So these are 180 millimeter square cells. We've seen different sizes within the industry moving to the 210 for a number of reasons that I'll touch on here in the further slides. We've opted for the 180 millimeter M7 cells, offering increased power, reaching that 530 watt range, and offering low temperature coefficient and lower LCOE to the customers. Now, these larger wafers offer greater power. Some innovations that we have employed are more of a wire technology as opposed to a flat ribbon that's used. This allows for more light to be reflected back onto the cell, increasing the module power. Multi-bus bar technology, which improves the light utilization and reduces CTM losses. And the half-cut cells, as I mentioned, which will lower the electrical losses and reduce potential hotspots. So this is ET Solar's approach and the approach of many others in the industry. So what have we done to manage the risks that are associated with the processing of these larger cells? So we offer advanced inline inspections. So there's a color detection after PECVD. So as the cells come out of the furnace, we're able to determine quality of each batch from the furnace level. So these cells don't move down further stream in the process of manufacturing and can control the quality. Also do inline print quality inspection and then inline integrated EL inspection. So this is to help ensure the quality of the cells as they move through the process. Now, one of the more, I guess, dangerous, so to speak, aspects of the larger format cells is the cell cutting. So ET Solar uses an advanced laser cutting technology, which effectively reduces the cutting damage on the cells. I have pictures here on the left with the traditional cutting approach. A traditional split section cutting leaves significant heat affected areas on the edges, degrading performance. That can be seen here. With ET Solar's approach, with the micro cutting, it effectively eliminates that heat area. You can see through the images the difference here. Now I'll dive a little bit more deeper into these, the cell cutting technology and the issues that are inherent and the advantages moving towards this novel micro cutting approach. So a typical split section cutting involves a laser ablation. So you're actually pounding away at the material with a high energy pulsed laser to cut a V-shaped groove into the cell. And then there's a mechanical split, a breaking apart of the cells. And this is the typical approach that's used in the industry. So there are some inherent issues with that, those being large heat effect area, which I showed in the previous slide. So the processing temperatures for those lasers exceeds that silicon evaporation threshold. So you get that damage to the material and a degraded performance. There's also some debris that is created from that ablation process. This introduces a dust and potential contaminant throughout the rest of the processes. There's the damaged silicon substrate, so there's numerous microcracks that are generated on the cutting section. These microcracks lead to a reduced cell strength, which can lead to further problems in the module. And there's a higher fragmentation rate. So as these cells are broken apart through a mechanical break, this increases the probability for catastrophic failure. So ET Solar has taken the microcutting approach, and this is kind of I guess it begins with a partially prefabricated groove into the material, plus a new thermal stress controlled fraction technology. So through a low power laser, could do a local irradiation to the area to be split. This creates an uneven thermal expansion within the material, which then in turn generates some unique tensile and compressive stress fields, and these can be controlled to instigate a crack propagation process through the cell. So some of the advantages to this novel approach for cell cutting is that it utilizes a lower power laser. The temperature is low and does not cause any kind of heat damage to the silicon. There is no dust generated. The material can be separated without the vaporization or any kind of melting process to the material. There are no microcracks or microparticles that result from the fracture surface cracks. And the cross-section is of good quality, high mechanical strength, which is extremely important when this is all strung together and put into the module. And then there are no mechanical splits required after the material is cut. There is an automatic separation from this process. So it highly reduces any kind of stresses onto the material. And I can show some additional photos here now of this approach. This is comparing the traditional cell cutting and the novel micro-cutting approach that ET Solar employs. So you can see on the left, there's a split section of the cutting. You can see the damages from the high power laser and how that affects the material. And then even a closer up perspective of that, you can see these fragments that are along the surface causing some weakness to the material, and that would potentially lead to further microcracks within the material. And on the right, we have the microcutting approach, and you can see the vast difference of that clean line that's created and no damage, thermal damage done to the cell substrate itself. We've done this both on the bifacial and monofacial cell. And one important note here is, as ET Solar has opted to employ the 180 millimeter format. Some module manufacturers are utilizing a larger format, the G12, 210 millimeters, or even beyond. And those processes that are associated with those larger format cells don't just require a half-cut cell, but they are moving towards a cell being broken into thirds, which requires 2 cuts. And this would mean that there are some inconsistencies in the process where at least one of the 3 remaining cells from that process will have cuts on both sides. And the uniformity issues could be slightly different from the other 2, where they only have a edge from 1 cut. So there are some various considerations that ET Solar took in terms of which technology for cell format to utilize. And in this case, we went with a 180 millimeter design.
All right, Craig. Thank you very much, but we do have to try to stick to our very packed schedule. Unfortunately, we have been running a little bit over time, but I do thank you very much for your incredibly interesting input that you just shared with us here.
Okay. Well, I apologize. I ran a little slow here. I wish I could proceed, but I guess we can go from there.
Thank you, Craig. Thank you very much. And while we heard a little bit about handling larger wafer formats in the manufacturing processes while cutting. Cell cracking can actually also happen after installation or during installation, as our next guests have found out during their research. Lou Triple is the Vice President of Product Management with First Solar. And Lou Triple will tell us more about what the company found out when they tried and investigate weather-related phenomena for cell cracking. Hello, Lou.
Hello, and great to be here today. Thanks. So what I want to talk to you guys about today here from First Solar is our perspective and how our technology selection overall can influence the severe weather risk profile and overall risk of PV plants. Quickly to introduce First Solar, for those who may not be familiar, First Solar is the largest thin film module manufacturer and the largest overall solar manufacturer in the Western Hemisphere. We have over 25 gigawatts of product that we've historically shipped, predominantly focused on the utility scale market, but moving into other applications in commercial, industrial, mid-tier markets and other product applications around the globe. As we look to the next slides, we also see a profile of our global historical shipments, which have spanned over 30 countries. We have manufacturing locations in the US, Vietnam, and Malaysia. So we can go ahead and skip to the next slide. We've been focused over the last couple of years primarily on our larger form factor Series 6 module, and in the span of ramping that production capability across the globe into our global fleet, have built and shipped over 5.6 gigawatts of that new product. So as we turn to the topic of interest today, as we just heard, cell cracking, as we move forward in the slides, it is a critical issue in the industry. This has been well documented. It's over the last several months and years become a higher profile issue. We have taken an active role within the industry to help try to drive solutions, understand problems, help react to some of our customers' concerns as they have been hit with challenges in their insurance coverages or overall financial risk exposure. We've also been active in the standards community as we believe that there is a place for stronger, more comprehensive evaluation of PV modules. While the standards today do an adequate job, there's much more that can be done in order to advance the industry as a whole. As we look at the next slide, overall, what you just heard from our prior presenter was discussion around cell cracking risk in the silicon manufacturing process. The portion of the risks I'm going to speak about today are much more focused on the field and what happens to modules after they leave the factory and the risk levels that occur due to high wind events, hail impact events, and frankly, just the simple act of mounting modules on mechanical structures, for instance, center torque tube trackers with narrow mounting positions, which can create a higher stress situation for modules just in day-to-day operation. So one of the things to keep in mind as we look forward to the next slide in corollaries to the building industry and a more mature industry. And as we look at solar, while we've made a lot of strides over the last decades plus in penetrating the global energy infrastructure, in a lot of ways, the industry is still immature. If we look to the building industry, we see very clear examples of how building construction and the material selection in those construction activities can directly influence the physical risks that occur due to natural disasters, for instance, fire risk, and how a wood-framed home or building has a different risk profile, a different categorization than a concrete or steel-framed structure. And the insurance industry has grown around that and created differential premium structures as a result of those differential risk profiles. The solar industry in the space of insurance is going through a change right now where the industry is still a bit immature and has not yet fully appreciated the differences between technologies. What we're looking at now is a view of First Solar's highly differentiated thin film module construction compared to the traditional cell-based crystalline silicon module construction that many in the industry are familiar with. First Solar is very different in that we have an end-to-end process that is fully executed under one roof. The primary physical difference is the utilization of a thin film semiconductor. That thin film, as pictured here, is 3 micrometers thick. That's less than the thickness of a human hair or the diameter of a red blood cell. In contrast, a typical wafer and cell in a crystalline silicon module is approximately 160 micrometers. What that different semiconductor material provides to First Solar's modules is an innate immunity to cell cracking. The material is inherently so thin that it simply conforms and complies to whatever substrate it is deposited on. In First Solar's case, that is a glass substrate. We utilize a glass laminate for our module. As long as that glass remains fully intact, that cell structure likewise remains fully intact, and so is inherently immune to the cell cracking risks that are plaguing the industry today. As we step forward and zoom in a little bit further, on the next slide, we see an illustration of how the thin film semiconductor material can be applied in flexible applications. While First Solar doesn't primarily manufacture that flexible type of product, those products do exist in the industry. Papers and studies have been written to document the inherent flexibility of a thin film cell technology like our thin film CAD-TEL. And so as a result of this, First Solar has developed and launched just recently what we believe to be the industry's first and only warranty against the hidden cell cracking phenomenon that is otherwise affecting the brittle crystalline cells that are common throughout the rest of the industry. As we move forward, what we're going to talk about today very quickly is a quick case study that looks at the severe weather risk and what can happen when you have 2 different module types in that type of environment. So as the slides advance here, we will first take a look at the hail risk profile that we see and look at that throughout the globe. Hail impacts, as we look at the maps on the next slide, show a significant geography that is impacted. We're very familiar at First Solar with the United States market and the central portion of that market with a very, very high risk profile, especially in the state of Texas, where significant numbers of projects are sprouting up. This problem is only getting worse with the specter of climate change and the impact that that's caused in the frequency and severity of severe weather events. The next slide illustrates, as we've been working on this issue throughout the industry, I'll cite a study and presentations from our friendly colleagues at PV Evolution Laboratories, or PVEL. They've presented multiple times in similar forums on what they present as a hypothetical scenario, but very well rooted in a reality situation that occurred just last year, where a very large scale utility plant was hit with a very high wind and heavy hail weather catastrophe. The punchline is, while we could all walk through that plant and we could see the devastation in physically damaged modules and structures, the real story is the hidden cell cracking. In this particular scenario, represented as a typical risk profile, the invisible cell cracking that can only be detected by advanced imaging techniques like electroluminescence was 4 times as impactful from a financial and damage standpoint. For crystalline silicon modules, this is a tremendously challenging risk. It's challenging for plant owners. They have to undertake expensive diagnostics to try to determine how much of their plant might be affected. And overall, this hidden cell cracking is probably the largest risk right now in the industry because of the combination of its expense when something occurs, its pervasiveness, and because of the changes happening in the insurance industry and the additional risk that that's bringing to project developers and owners. As we look more specifically, as we advance to the next slide, at a study conducted at Certus Solis, an independent laboratory, we look at what differences those module construction changes or different module construction types that we outlined at the start of the presentation, what those result in as we look at laboratory testing. and I'm not sure if we're seeing latency here or if we could advance to the next slide, please. But that study was focused on trying to illustrate the differential between First Solar's thin film cadmium telluride module construction and both monocrystalline and multicrystalline silicon modules as they're impacted by a combination of 45 millimeter hailstone, then followed by thermal cycling and humidity-free cycling. Again, if we could advance to the next slide. Thank you. So in this study, what we show with the green line at the top is First Solar's module after 3 consecutive sequences of an IEC-compliant hail impact test at 45 millimeters, 50 thermal cycles, and 10 humidity-free cycles. We see First Solar's modules exhibit 0 measurable power loss after 3 sequential applications of those stresses, while both monocrystalline and multicrystalline modules show physical cracks, which can be detected via electroluminescence, as shown on the bottom right, through those progressive stages. And we can also see through that Certosola study the progressive power impact loss as a result of those stresses, 3%, 6%, up to an average 8% output power loss after those multiple stress sequences. The IEC standards that are out there today provide a basic level of evaluation, but they do not apply the thermal stresses that you see here, and so have a blind spot relative to the long-term impact when modules remain exposed after being damaged by a severe weather event or otherwise impacted by microcracks. So as we step to the next slide, what First Solar has been able to do with its uniquely differentiated technology and with its inherent immunity to hidden cell cracking is we've developed a warranty coverage that allows our customers to take advantage of that. We are warranting the both workmanship and power output impact that could be caused by hidden cell cracking, and do so for those scenarios while the glass remains fully intact in our module. We are guaranteeing that the cells in our module remain free of cracks and mechanically intact, and providing the output power that we have stood by for over a decade. So this coverage has a significant value in all projects across all regions, but most specifically and acutely in areas where you have exposure to severe weather or severe hail impacts. So in conclusion, as we close out with the final slide, just reminders that the hidden cell cracking phenomenon is something that affects crystalline silicon modules and can't be seen by the naked eye. Major risk in terms of power and energy production loss. First Solar modules possess an inherent immunity due to our unique thin film construction and possess an industry's first and only hidden cell cracking warranty that we're proud to discuss with any of our customers going forward. We feel that the thin film CAD-TEL modules from First Solar provide a positively differentiated technology that can be utilized to lower risk profiles in PV plants as a result of severe weather events. Thanks very much. Lou,
for your interesting input, and we will be moving on now as we have been hearing about 3 different ways to address various module-related failures and ways to address that. And I think now it's time to sit down for a chat with one who's really seen it all, George Touloupis from CA, everybody.
Join you at this juncture because we are getting a lot of questions from our attendees, and our next guest really has an eye on quality right across the supply chain and particular expertise in modules. George Touloupis is, I believe, the Director of Technology from CEA, Clean Energy Associates. So George, please join us on the stage here. I'd like you to welcome you to this Quality Roundtable. And if you will be willing to, George, can you address some of the questions related to the presentations that we've just seen that have come through to our panelists? So George, without further ado, I want to just run you through a few of them. I know that you're always monitoring technology, always monitoring module manufacturing, cell technologies. So we've got some relevant questions here, and if we can do a quick-fire Q&A round, I'd be much appreciated. Okay, so without further ado, we've heard about cutting larger cells into perhaps 3 pieces, these very big wafer formats. ET Solar said some manufacturers were doing it. Have you seen any concerns, or do you have any concerns with regards to cutting these very large wafers into 3 parts?
Yeah, sure. Good afternoon. Thank you for having me here. So what Greg's described, the ET Solar way of cutting the cells, damage-free cutting, is something that is absolutely needed for bigger wafers, and especially the 210 millimeter cut in 3. So manufacturers are aware that the current way of cutting cells might be okay for 2 pieces or half cut, let's say, and a small wafer, but it is not okay for the big wafers. That they have to cut in 3 because that's how the optimization works with the current resistivity losses and the CTM loss. So yeah, that's a great direction. Technology is mature, it's there, and I think as where manufacturers are going for higher efficiencies and more reliability, there's going to be a move towards damage-free cutting.
Okay, damage-free cutting being one of the key terms there. We have a question also about gallium-doped solar cells. Are they really being manufactured at scale at the moment? And do you know, is there a price differential between the gallium-doped and the boron-doped cells and modules?
Yes, I think gallium is a well-hidden secret that's been around for many years. Now it's out. And there are well-known issues, and I think we've had a couple of articles, very important articles in the recent issue of PV magazine where it was very well explained. So gallium is inherently more difficult to manufacture, control the resistivity. So you have a yield problem, and this is the cost issue. So as soon as this is controlled, and Longi has done it, it's the proof that they have done it is that they're offering the gallium-doped wafers at the same price. So obviously their cost must be the same. So as soon as it's done, yeah, there's no cost issue. Reliability-wise, if you take LID, yes, it's true. It's very well known that there is no LID when you dope with gallium because you don't have the boron-oxygen and the iron-boron complexes that are responsible for LID. LETID is something new. We're still looking at it. We haven't seen enough data to be sure. And from CA's own batch testing, which is testing lots of production, we have seen abnormally low LID in the past, a couple of years ago at least, back, almost 0. And we're pretty sure actually there were gallium-doped wafers. So yes, it is 0 LID. You can actually see that happening. Very big differentiation between boron-doped batches.
Okay, well, that's a good result, it seems. In terms of, can I jump to LETID?
Absolutely, yeah.
Thanks, Marian. LETID was also mentioned in the Longi presentation. What about N-type modules? Are they less affected by LETID? And how could N-type perhaps, on that basis, compete with these gallium-doped P-type cells and modules?
So, 2 issues here. It's a complicated question. The answer is going to be complicated as well. So to make things clear, LETID is not like LID in a sense that if the recipe is corrected, you can have LETID-free modules, period. It can be done. It has been done by the pioneers, by ANWA. So the know-how is kind of still a bit secret. There is a shroud of IP and special recipes, but it's doable, and people are learning how to do it. So it can be mitigated almost fully. LID is a different story because it's inherent in the composition, the doping of the wafer. So yes, gallium makes a big difference for LID. I do not know, I'm not familiar with the mechanisms that the way that the gallium doping influences the LETID. Certainly, researchers have seen that LETID can affect any type of wafer, including float zone and N-type. So again, it's a matter of tweaking recipes and making it disappear, basically, which is doable. It's a matter of know-how. So eventually, manufacturers will get there. What gallium doping is doing, though, which is very important, it is that it is taking a big advantage from N-type platforms, which is the zero LIT. So this is going away, and it has a huge financial impact on the modeling. So this 2% initial year, it vanishes. Of course, they are not giving the warranties yet, but eventually they will,
Okay.
because the physics are there.
Indeed, the fundamentals are there. Okay, George, thank you very much for your time. George Taloupas, please stick around. We have a panel on floating PV coming up very shortly, which you're going to be taking part in. I'm really excited about that. We are running a little bit behind schedule. Our next presentation coming up is addressing power electronics, which is a key area of concern in terms of quality of PV projects. It's also an area that Marianne writes a lot about for PV Magazine. So in just a few moments, we'll be speaking power electronics in particularly challenging environments. George, I'll be speaking with you soon.
Exactly. Well, turning our attention now to the field of power electronics, and the Italian manufacturer FEMA has placed a couple of solar arrays in Antarctica and in other very challenging places where you really wouldn't expect to expose power electronics or any other form of electronics out in the open. Their chairman, Filippo Cazzaniga, is joining us today to tell us what the company has done to qualify and validate its products and rest assured that the device or the array will stay secure in Antarctica. Hello, Filippo.
Hello, Marianne, and good afternoon. Thank you. Yeah, I would like to start my presentation with the first slide and one number. That is 94. I don't want to give you a sort of complicated presentation about our company, but I think that just with one number, 94, that is the percentage of solar business of our company. And why it's so important to have a so strong focalization in the solar business, because when you are focalized on a business, especially solar that is changing so fast and so frequently, you can be very focused on your business and you can put the customer and the quality for the customer in the center of your business. Of course, with the integration of ABB, we increase drastically our focalizations on solar. It was strategic, of course, and with the integration of ABB, we are going to increase even more our skills and our experiences in quality. And how we are going to do with our people, because what we are doing now is to integrate the two companies and integrate all the people that are working with us. How? Because we have a lot of experience in solar, and we are all the peoples that we got from ABB have a lot of experience also, but in different market and in different segments. What we are doing now is to integrate all the experience, all the background into one company, definitely. And we are putting together all the ambitions and all the experience of all the people into one company to shape a new identity of the company. And how? Because we are merging also different cultures in addition to different experience. And that's everything is focused to increase our quality and the quality of our product. How we are increasing our quality of our product in different stages, during the designing, during the manufacturing, the productions, and during the entire lifetime of our product during the installations. We are putting together different elements into the acquisition and the integration. Because we found some very important and key elements into the company that we acquire. So a very strong focus in R&D and also in all the quality processes of R&D, of course, to have a global footprint that is one of the key elements to guarantee the quality of your inverter and of your equipment, especially when installed, because thanks to the global presence, you can maintain very strongly your inverter into the operation time. And reliability and quality, because we found really a lot of equipment and experience, especially to increase the quality of the inverter, to increase the quality of the power electronic, and especially to test the quality of the inverter in the entire lifetime with a lot of tests of accelerated lifetime, and I will show you later how. But we need also to put together other elements, typically of a smaller company, like, for example, speed, focalization into the business that I was telling you before, and flexibility, because just some of these key elements are not enough to be successful in solar. And what does it mean for us to be successful in solar is to put at the center of our business our customers, of course, our partner, and especially all their needs. Now, you might wonder why I'm showing you the penguins now, and I'm going to the topic of this panel, because that was the Uruguayan research-based Artigas in the Antarctic, and is a natural laboratory for all the tests on the environmental research and to understand how the global climate is changing. And it's a very hostile environment because we are facing temperature of less than minus 40 Celsius degrees and winds of over 200 kilometers per hour. So we are definitely in an extreme situation, and we are operating with our solar inverter in this kind of situation. And how we do that? Thanks to all the equipments where we invested in the past years, especially to test the power electronics, because one of the key elements of an inverter is that the inverter is not a passive element, but is an active element. So we are taking energy and we are transforming the energy. And to work in particularly strong situations, strong environmental situation like this one, is one of the most critical part of our job, because we can face situations like Antarctic, so with very strong winds and very rigid temperatures, but we can face also completely different situations, like I will show you after this slide, that are completely desertic situations, so where with dust, with powder, and with one of the highest temperatures that we can face. So an inverter must work in both different conditions, and also on the floating, of course, so with a very high humidity, operating humidity. So how we are facing all these kind of challenges just to increase our level of testing our inverter. And we are testing our inverter in the designing phase, because it's important to design inverter accordingly of what will be the applications during the manufacturing, because if we are not testing the inverter properly during the manufacture, we can face problem after the installation, and of course during the entire lifetime, so all the maintenance. Our mission in this case was to increase our quality level in partnership with our customer, just to supply to our customer not only an inverter, but mainly a solution of their needs. They had a need to install an inverter and a solar plant in so rigid condition, in so strong environmental condition, and we need to find a solutions to match the customer needs with our availability and our quality. The challenge, as I told you, was to install the second Antarctic solar project, because the first one has been done a couple of years ago, and we did it in 3 days. The partner was the Istituto Antartico Uruguayo and the Ministry, of course, of Industry and Energy. And they tried to test, of course, FEMER technologies, saving time and resources, because we already installed this kind of inverter in a such difficult environmental situation. and with an extensive training in real time to support the installer in that condition, of course. What was the result? A 10% of total power demanded in solar generating during summertime, and up to 4 tons carbon emission offset already till the end of March. 1,415 days of TV, offset of equivalent up to 1 hectare of pine forest, or up to 40 computers power for one year. And now we are going to a completely and as well extreme situation, as I mentioned before. This is one of our biggest installation. It has been installed in Mexico. It is the biggest plant in the America because it's 830 megawatt in a completely desertic area. This plant have a peculiarity because it's changing very in an extreme way the conditions during the summertime and the winter, because during winter we can face snow in the same installation, and during summer we are facing winds of 130 degrees and temperature of more than 45 degrees. So we are in a complete and opposite situation respect to before. And what we faced in this situation, in addition to the extreme temperatures, we faced the protection of our inverters against dust, powder, and sand, of course, because all the winds of 130 kilometers per hour are generating a lot of sand and a lot of dust. So that was a very particular condition where we had to study particular filtering system for our inverter to work properly. And this has been done to test all the conditions of our inverter in our laboratories that I will show later. But we have also different installations in other different environmental conditions. For example, in Mont Blanc, where we installed our inverter as 3,000 and more than 450 meters above the sea level, so in a very extreme high conditions, or in Singapore, where we have an installation, floating installation of more than 100 megawatt that is working properly, but with all the high humidity conditions that are typical of a floating installation. All of those is possible thanks to the investments that we did in our laboratories. We have laboratories for testing our inverter, of course, in Helsinki, where we have the biggest research center for the utility scale solution, central inverter utility scale solution, and it's called the Sahara Laboratory. Then we have a full set of laboratory and testing facilities in Valdarno, where we have all the manufacturing of our string solutions, and then in Vimercate, our headquarters here in Italy, where we are testing inverter. But what are the peculiarity of our laboratories? Especially in Finland, we invest so much in the past year to have a very complete laboratory to test the inverter in all the possible conditions that we faced in every situation all around the globe, and especially in all the grids conditions. We can reach a power up to 8 megawatts, so a full power of our inverter. We have a climate room. I think it's one of the biggest climate room in the market for sure, to test the inverter starting from minus 50 degrees up to 150 degrees, and with a shift of 1 degree per minute. So very strong challenge to test all our inverter in every conditions, thanks to the equipment that we equipped our laboratory, of course. And in addition, we can test, of course, all our inverter in every grid condition that we can face. Thanks to these investments that we did in the past years, we can face all the conditions that are expected for our installations. And so you're ready, yes, of course, because the progress only happens when you are pushing your boundaries. And we offer to our partners, as I told before, a bold combination of flexibility and reliability, because are all elements that we put together thanks to the acquisitions, because we have some elements and we found other elements that are all putting together the key elements to be successful in this market. And our advanced and solar EVI, so electric vehicle charging solution, help to push the limit at what is possible. So we are really focused. We have a strong investments in R&D, strong investments in quality and processes, and also in the service experience. So together, let's step into a new era in solar. Thank you, Marian.
Moving forwards with our program, and we have coming up a panel discussion on floating PV, and now it's also your time to get your questions up to us. Jonathan will be moderating these questions and bringing them to our experts.
Indeed, and as Marian said right at the top, floating PV is really one of the fastest growing applications. I think 150% annual growth 2019 to 2020 as found by IHS Markit. So it's a very exciting opportunity. East Asia is a big growing area, but Europe as well. There are a number of applications in Europe growing very quickly. But of course, PV on water isn't a natural application. There are many risks with electricity on water right across the supply chain. So from the mounting structures to the power electronics to the cabling and connectors modules themselves. So we're going to touch on a number of these in a panel coming up. Well, absolutely right now, in fact. Marian, can you introduce our panelists?
I can. Well, we have from the Netherlands, Minne de Jong. He is a solar application specialist with TNO, a Dutch research association, who's been doing a lot of testing and validating of solar floating systems. Hi, Minne.
Good afternoon. Nice to be here.
Thank you. And we also have Eric Ast, who is from Stäubli Connectors. Thank you, Eric, for joining us today.
Hi, Marian. Hi, Jonathan.
And we have Ben Macias from BOS supplier Scholz. Hi, Ben.
Hi, how are you? Thanks for having us.
Very good. Thank you. Thanks you for joining. And again with us from earlier, Craig Snee from ETS Solar and George Touloupas from CEA. Thank you so much for joining again. Well, outside of Asia, one of the largest markets for floating is the Netherlands. And Minne, you've been working at a new research facility in Rotterdam and did a lot of testing of various solar systems there. What is your impression? Just a quick fire introduction answer. What's your impression? What are the most important quality aspects that the industry needs to consider moving forwards from here?
Well, I think as this is a rather new field, there are a lot of things that we haven't seen before, and I should say we have a test facility for floating PV. Which is sort of aiming for the next step. So we now have a rather large, number of systems are being built in the Netherlands, and the portfolio for systems that are going to be built is rather large too. But these are all, inland, easy lakes, quiet lakes, you could say, a lot of sand mining areas. And now we're preparing towards moving to more challenging waters. So larger waters where there will be more wind, there will be more waves. Some of them may be salty or brackish. And this brings very new challenges to the PV field. We need to consider what exactly we need here. What we've seen so far is that from the challenges that we have, waves are the most difficult one to tackle as for now.
Okay, thank you for this introduction and assessment. Connectors are among the more frequent failure points, as we've been discussing at this Quality Roundtables also in the past. Eric, how is Stäubli preparing for the challenge of tapping into the floating market? Is the standard MC4 good enough for floating, or are you testing and validating and developing a new bespoke product for the future?
Yes, Marian, you're right. So MC4 basically is enough and already fulfill the requirements. Basically, it's important to know that there is no standard, right, for floating PV. There's a work in the IEC, in this TC82 committee, working on standards for floating PV on the component level, but also on the system design, because we see here all the things we already mentioned during the previous quality roundtable regarding the best practices for installation are valid also for that. An easy example, when people are bringing the modules on the structure to be assembled and put on the structure, you have to take care that basically the modules are coming with protective caps, and then that you immediately just plug the connectors together to avoid humidity to come into the connector is very important. And what we did to let's say improve or ensure that our product is adapted to this application is we are testing beyond the norm so that the connectors fulfill salt mist spray, ammonia resistancy, etc.
Okay, thank you, Eric. And you said the keyword of handling the installation job correctly and according to the best practices. Well, that leads us right to our next speaker from Scholz. The Big Lead Assembly promises to improve or make easier the installation job and combines various BOS components into one product. What's the value proposition for this one in floating installations, Ben?
Yeah, so the benefit for onshore for the BLA, the Big Lead Assembly, is it's an above-ground cable management system, a trunk cable that eliminates the need for trenching and significantly induces velocity of the install. As far as floating PV, a lot of that is done on a very modular basis. So the cable can be deployed on its particular floating device and then driven out, or I'm sorry, taken out by boat to attach to the existing array as they're building it. So for the BLA, really no change there. It's actually IP68 rated, and it can be submersed. We've done some testing, 1 meter, 1 hour, up to 240 hours under 1 meter. So the product works onshore as well as floating.
All right, thank you very much. And Craig, we have heard earlier from you that your new manufacturing sites are in Southeast Asia. The largest market for floating PV. Has ETS Solar done anything to tap into this market?
Yeah, we have. So unfortunately, I didn't get a chance to touch on a case study here where ETS Solar has participated in a 10 megawatt floating solar project in Liaoning, China. So we went through numerous iterations in terms of design and trying to employ the best, most durable solution for this type of application. And what we found is through numerous testing efforts and working with partners such as VDE Lab to verify the module is to go with a dual glass design, which provides mechanically a better solution with glass on both sides of the module. And then it also a frameless design, which eliminates the PID effects. So those are the two major considerations, water ingress, durability, and the PID effects that can degrade performance over time. So going with a frameless design, dual glass design, the modules are able to surpass the DH3000 test, or the dual damp heat test for over 3,000 hours, and qualified the module to rate for an IP68 qualification. So as Ben just touched on, enables us to actually perform well in a wet environment.
Thank you very much, Craig. Well, George, you just got a short glimpse of what a module manufacturer is doing to prepare to go into the floating PV market. What do you want to see from your standpoint? What do you want to see from module manufacturers and other component suppliers to make sure that these investments ensure a long-term performance?
Sure. First of all, it's still baby steps. I think it's only a little over 1 gigawatt compared to the 640 installed of land-based PV. There are no standards. Everybody is more or less not scratching their heads. I mean, there is some definitely development investment. And TNO is doing great work in very difficult conditions with salt brackies, category 4. By the way, I've met Dr. Krohn in Singapore at the Floating Solar Symposium. I was very impressed by the work you Dutch are doing, trying to put PV in sea. So yeah, there's a long way to go. And unfortunately, there are no rules. I mean, even this conventional wisdom that double glass is better doesn't necessarily apply. If you talk to Ceres in Singapore, they have a floating testbed. After 2-3 years, they don't see any advantage of glass with respect to glass backsheet, provided, of course, that the backsheet has certain specifications like low water transmission properties, etc. So there is a tremendous amount of work that we need to do. The World Bank has published the handbook for practitioners, which is a really good work, and it's kind of crowdsourced by experts. So things are going fast in that direction, but we need projects to understand what's going on, because even very experienced installers and floating producers like Cieleper, they had such big mishaps, like the fire and water in Japan. And that was due to anchoring, by the way. But again, anchoring is important. So we're still learning, everybody.
Indeed. Thank you, George, for sharing those insights. Now some questions from our attendees. Eric asked from Stoibli, I think this first one I'll direct towards you. It's a little bit of a skeptical tone. It says, floating PV, DC electricity close to tons of water. Does this really work over the long term? I suppose this comes down to, can you really insulate these cables and connectors for such a long period of time when you're in an aquatic environment?
So the thing is, the DC connectors should not be in water. They are tested, they are approved for being in water for 1 hour, 1 meter. So they are AP65 tested and approved, but it should not be in the water. And we know that some of the requirements for a standard PV application, like UV resistance and so on, is even more important on water, because you have the water reflecting those, etc. But yeah, we test far beyond the norm, and as long as those basic requirements are fulfilled, we do not see any issue with our connectors.
Okay, interesting. Well, of course, connectors are key to kind of durability, and as other module materials, as George kind of hinted at. I think this might be tackled perhaps best by you, Craig, in terms of it's asking about module manufacturers and warranties for floating PV sites. Are you aware that module makers can provide, or a module maker like ET Solar can provide a warranty for floating PV applications, or do they differ?
From my experience, there hasn't been really a difference in terms of the workmanship and performance that's guaranteed. Module workmanship is for 10 years. The performance is 30 years on newer modules. So there really hasn't been any significant change there. There is third-party warranty that we offer that will back performance over time. So that might be an addition to a standard approach. But really the BDE lab testings that we went through that qualified our modules for the IP68 standard, exceeding the DH3000 test, which exceeds the standard DH2000 test, really helps to ensure the performance, and the lab results support that. So that's been our approach, but I guess we're always open to discussions on the topic.
And George, do you have anything to add on that in terms of warranties for modules on water from CEA's standpoint?
So what we've seen is that manufacturers that want to provide modules for floating projects, they have to strike down all these limitations, the limited warranties, because, yeah, of course, they can't be there. And they do it because there's no other way that they can supply the modules. But the point is not the warranty. The warranties have to be what they have to be, because the projects must be bankable. It's reliability. And this is the biggest if there. It's a warranty is an easy thing. It's commercial decision in the end, right? but will this module last for 25, 30 years? And what do you have to do to make it last? What does damp heat 3000 mean in IP68 in 30 years? And what kind of conditions as well? It's not all flouting sites are the same. There are big differences, and the flow design can have a huge impact can have much bigger problems than what the module can give to you, including cabling, etc.
Okay, we have some performance questions. Marion, would you like to jump in?
Absolutely. Well, we heard that there's different connectors or different salt water ingresses for different parts, and I would direct that question to Minne de Jong, who has tested some of these materials in brackish water at least. And what's your experience for long-term exposure of such an environment on these products?
Well, first of all, I should say that a typical field test does not have the same length as the lifetime of a typical installation. So we monitor for a year or maybe two. And I think we should make a distinction between, short-term catastrophic failures, so things that go wrong because of ill design, and things that go wrong due to wear and tear or constant movement or ingress of water and salt. And of course, because of the nature of these outdoor tests, we mainly have experience in failures that occur in the first year or the first two. And when we talk about the reliability of connectors or junction boxes, we have indeed seen a few examples of junction boxes where there's definitely ingress of water and salt, and you have corrosion there. We've also seen some connectors that fail, but it's not always clear what causes that, because you have this corrosive environment, but you also have this constant movement, and we've seen some examples where constant movement together with a design that could be improved resulted in damaged electrical components.
So it's really the constant movement of the floating platform that makes the cables move and progressively damage the junction box.
I think for the junction box, it's really the environment, but the junction box does not really move with respect to anything in its surroundings. But I think when you talk about cables and the connectors, I think constant movement could be a problem. Yes.
Okay, well, let's bring Scholes into the conversation as a very big kind of BOS supplier. This is kind of everything but the module or the inverter. What about corrosion then in these kind of environments? We have a question about galvanic corrosion in such a corrosive environment for metals. Do you think this can be mitigated I imagine by coatings, but how can this be mitigated?
Yeah, so I would say about 99% of the junction boxes that we manufacture are made with fiberglass. They're an IP65 rated product. So, to mitigate any type of corrosion, I would say non-metallic enclosures are probably best for this type of environment. And wanted to hit on what Eric said earlier about connectors. We deal with quite a bit of connectors. Inline fusing, overmold, cross junctions. So very important to understand that these connectors are not made to be submersed for long periods of time. As Eric mentioned, standard testing is 1 meter, 1 hour. We recommend that across the board to all of our clients. And one other thing I want to hit on is always make sure and ensure that we are not cross-mating connectors from different connector manufacturers with each other. There's a huge problem with that on shore. So you take that same type of situation where everybody's using dissimilar metals and you plug them in together, they might seat together, but they're not always have the correct critical dimensions. And now you take and add some atmospheric moisture and salt to that same situation, could lead to some big problems for these types of applications.
Yeah, and there was actually a specific question about the salt exposure and connectors in a potentially aquatic environment. Would that concern you?
Definitely. It's probably, you're adding contamination to contact, just like when we have these large desert fields, if the connectors are not sealed and immediately plugged in after the caps are removed, contamination will lead to failure. It's not a matter of if, it's a matter of when.
Yeah, absolutely. Okay, a key kind of installation insight there. Eric, would you like to add anything on that from the connector standpoint?
Yeah, what Ben mentioned is absolutely correct. But considering people selecting the right components, then to use them properly is also very important, because you can select the best connector, you can select the best component, but if you don't have the appropriate cable, if it's not assembled in a proper way, creamed properly and torqued properly on the cable, you might have an issue also afterwards. And Mine mentioned some of the issue that the parts are moving constantly. We've seen that also onshore, while wind and other effects happens. We've seen cable that were just moving to the structure to a point they were cut at, or the insulation material was just degraded, and we see a failure coming. So yeah, Ben did say it very well when saying the question is not if, the question is when.
And what about the standards discussion? Are you aware, another one of the questions is about standards in terms of floating PV. Are we making progress there?
We are involved and part of one working group in the IEC world working on that, yes.
Okay, excellent. Now, can we turn back to the module for just a moment?
Absolutely, yes.
George, we have a question from George Talupas from CEA. We have a question regarding frameless modules, because as you said, a lot of floating installations use a double glass module. The question is, can a frameless module be used in a float structure? My apologies. And how about the grounding system for plant protection from far away, or like from sea to the water area? That's what I said.
Yeah, frameless glass modules are like one solution that is I've seen applied, but also, as I said, framed glass battery modules can be applied. So that depends on the flow design. It's a financial consideration as well. And then regarding PID, because that's the main consideration, that having frameless modules doesn't mean that you don't have PID. You have less, but you still can have PID. So the PID can be a huge problem because of the constant exposure to moisture. So maybe one solution is having string inverters that apply reverse voltage, so they mitigate the PID. No matter how big it is, you don't want to have this factor there, which can cause a lot of degradation, a lot of headache. So the inverter selection is a very important selection for floating PV projects. And I know that some inverter manufacturers that are very good in string inverters have presented quite comprehensive solutions and very strong arguments to that. So that's a long answer.
Okay, and just one final question, which is quite a general one about floating PV, not directly about quality. What kind of yield increase can we expect? I suppose TNO's in a good position to answer that because of your testing beds. The cooling effect is often spoken of. What kind of power output boost can we expect? Mini from TNO?
Well, there's been several stories on that, and I've heard some very wild numbers, up to 10 or 15%, and I think we should throw these away, because even if you make some very basic calculations and temperature effect of 0.4% per degree, and you would cool a lot, then 10 or 15% more would be, well, it's too good to be true. So we find numbers in the order of a few percent. And I know that Sarah's from Singapore has also been working on it. And at the moment, we are writing a publication for the special issue for solar energy that will come later this year, where we will publish our findings together. So that I think that will shed some light on this matter. But to manage some expectations, we do not find super spectacular increases there.
Okay, it's hard to quantify, but not super spectacular.
You'll read about it.
Great. Well, I'd like to thank all of our panelists for this discussion about the exciting area of floating PV that's exciting, but also does not come without pitfalls. Gentlemen, thank you very much for your time. And moving forward, we started with the OKI2 installations, tracking in the wind. We've been through a host of module technologies in terms of quality. What's your key takeaway, Marian?
Well, it really is that the industry has done its own work, and we have seen the various wind tunnel laboratories putting forward solutions to enable designs that live off bifacial modules arranged on a single axis trackers. You just have to follow it, and so that's really the takeaway, that the industry should move forward and make use of these torsional locks or the increased damping or the modulation of the natural frequency, and yeah. That works. So what's your key takeaway from the discussions that were ongoing today at this session?
Really wide-ranging, and I think the high-level one is that a lot of work is still being done on PV quality, which is really encouraging. Whether that's new cell cutting techniques for these larger wafers, whether that's gallium doping in the fight against LID, some of these new inverter applications in very extreme environments, and also the ongoing work in floating PV. Much work still to go in that field, but it is looking really promising. Marian, thank you very much for your work on the Quality Roundtable today. Thank you for your attention. I do hope you enjoyed it. I also want to encourage you to continue to use the event app platform to engage with our speakers. We do have a Meet the Speaker session with a number of the speakers here today. They'll be online. You can meet with them. There's one-to-one chat function as well, a group discussion. So a heap of activity there you can take part with on the event app. And I don't want you to go away either, because tomorrow we have two new roundtable sessions. For the first time, we're bringing you the Sustainability Roundtable, which really looks at the challenges facing the PV industry as we scale towards multi-terawatt scale, and how that makes sustainability not only a nice to have, but absolutely vital for our industry. And also our market session, which will look at new market opportunities in light of this post-COVID economy. And of course, COVID has meant that we have to stay this distance apart and also online, but it's been great to be able to engage with you and bring you these discussions here today. So on behalf of the PV Magazine, thank you very much, and please, I look forward to you joining the discussion tomorrow.